Hi, this is a screencast walkthrough of Chapter 5 of Applied Statistical Analysis for Psychology and Human Factors in our graduate course. I'm Shane Mueller, and you can get all the information from this website here. There's a link to this on the page. So we're talking about Chapter 5, which covers graphics. And to follow along, you can go to this website, download the supplemental materials for graphics. In fact, this is the advanced graphics materials. If you open up here, we're going to use this file. We're going to use the walkthrough file, and we're going to use these images. So download those somewhere where you can have access to them. I've downloaded them here, and I've also extracted my images into its own folder. So the images should be in a folder called images within this, so that you so that the R Studio can find them when it's looking for it. We're also going to be using several downloadable libraries, and I'll show you how to install those as we get to that point in the lesson. Let me just start by clearing all this out. And so you can open your walkthrough, and the first thing to do is to go to session, set working directory, so that it's looking in the same folder as this lives in. Okay, so we're going to talk about more advanced graphics. The previous chapter talked about some of the basic graphics methods that you can use, and we're going to talk about some more advanced things you might want to do, more complicated graphics. And the first thing to look at are something called dot charts. But actually, the preface to dot charts are pie charts. There's a lot written out there about pie charts and how terrible they are. These are pretty bad, but they're not as bad as these 3D pie charts you can see, which then place us in an angle. There's a lot of reasons they're bad. Our eyes aren't good at measuring area independent of length, and so that's one bad thing. They also take up a lot of room for the data they present. It's hard to, if you have two different series to compare, it's hard to compare them directly other than by color. It hides the numbers. It doesn't show relative, absolute size as well as relative. So there's a lot of reasons you might want to avoid pie charts. And for example, here's a pair of pie charts. We have two different distributions of pets that were either sent to the pet cemetery or the pet crematorium when they died. And so what does this make difficult? Well, the colors match and the labels match, but it's a lot of effort to try to figure out which one's higher over here. You can't look at them both at the same time. They're not on the same axes and things like that. So what's some alternative? A lot of the problems with this can be avoided with a stacked bar graph. We did that in the last chapter, stacked bar, because now the size is directly related to the height of the bar. To do that, to show you that, I'm going to make a matrix. cbind combines two vectors by column. So if I look at data now, you can see I've got the same numbers in a matrix, and I've labeled the rows and columns because the graph, if it's good, will use those automatically to label them. So let's make our bar graph. This is this shows really the same information. I think, let me clear this because I don't think I want two columns. This shows basically the same information as the others. It also shows a scale over here, so I can know how much that counts for. Oh, it's only 30 total. It's not 300,000 pets that I'm measuring. It's just 30. So it's, maybe 1 month at one cemetery and 1 month at one crematorium. So that tells you that type of stuff. At least ordinally, they're in the same order, so we can tell. We could put a legend up here, but I'm gonna do something a little different here. I've got these. I've got it started out with I guess these values, and if I use the function cumsum and I use apply to apply it to the second argument, let's see what that looks like. Now I've essentially applied cumulative sum to each column. And so what was 3, 5, 9 becomes 3, 8, 17. This is actually going to be where these dividing lines between each cell are going to be. So the one line I found what those are. And then I'm going to do a little trick where if I want to draw a label here, I want it halfway between this and this. So I'm going to take one vector, which is all the lines, and I'm going to add a 0 to the bottom of it. And another vector, I'm going to add a 0 to the top of it. And I'm going to average the two and then take the bottom n items. That's what I did here. I took sort of r-bind y-val 0 adds 0 to the bottom. R-bind y-vals 0 y-vals adds to the top. So if I average the two, you know, the first row is going to be half of 3 plus 0 over 2. So add up, divide by 2, and only take the first 6. That will find the midpoint of each cell. So I can then use that to place the labels. So that was really handy to do the layout of that. I could have used a legend as well, but this makes it really direct. You're looking exactly at the cell representing it. So here's an alternative to a pie chart that represents the size, the relative size, but does it in a way that's aligned with how people see things, and it's better for corresponding series. But it's still not great because I still have to sort of, you know, like they don't start at the same point, they don't end at the same point, so I still got to sort of use a calibrated eyeball to look at this and see if it's bigger than this and hunt and find the right one. So what a lot of people have recommended is to use something that's started to become known as a dot chart, probably for no really good reason. And a dot chart is just a line chart with categorical axes. So you put each one of these on a different level of an axis. And typically what you would do is put the category, or what you think of an independent variable, on your y-axis or your vertical axis. So I'm going to add a couple adornments to this to see. So now I've placed this as the independent variable, and each sort of row shows sort of slides. This dot slides on this line left or right to show you how much of that there is. So this can represent really nicely comparing two distributions, just like those pie charts did. But now I can really see how rock is very different, durables is not too different, and so on for the two different series. What this misses is that adding them up to the same number. You could probably do some normalization to try to address that as well anyway. So this I did by hand, and I did it with a matplot. Now matplot by default will plot series by row, but I put my data in the first, which is usually the x, and I put 1 through 6, which is sort of my y label in, or what would have been my x label in the y. So that does a matplot vertically instead of horizontally. So that's a little trick that you might try. I've done specified the x and y coordinates. I want to circle here, and I've turned on the x and y I've turned off the x and y axis here, so it just doesn't plot them. So if you look at what happens when I do this, it plots nothing, just a blank cell. I have the x label here, but I don't have a y label. I want to add those later on my own. Type O is a way of specifying that I want lines plus symbols, and I don't want any gaps between the lines and symbols. I want it solid. And line type, line 3 specifies, I think, where I want, how far below the box I want this. So we've done this before. I'm going to plot all of these sort of tick lines with one command segment. So they all start at 0, then I do 1 through 6 for the y values, and then I end at 10, and then do 1 through 6 for the y values, and that plots all 6 of those. All right, I was interrupted there for a moment. So we made all these lines in one swoop, and then I'm putting the axes back on so I have much closer and better control over what they look like. I'll add a legend so I can put it exactly where I want it, the title, and the axes. So I've got all the pieces sort of build my own dot chart. We'll use that later. I guess there is a example or a problem that asks you to use this. There is a dot chart that comes built in to R, and it looks like this. So it does basically the same thing. I don't like it as much. First of all, if you have multiple series, it separates them. I don't think there's a way to making them, and it doesn't draw the lines between them. So it's really simple though, so that's nice. So let's see if we can make this work for a real example, a larger example. And what we're going to look at is a set of data from the US Senate. And this is, I think, from mid 2000s, a set of 19 votes that were identified by the labor union as votes that were right or wrong, in support of labor issues. So here we have a data set. We've got the name of the senator, their party affiliation, and then on 19 different issues, were they right or wrong? So we want to see maybe we can plot. Not this is no longer a pie chart, but it's a way we can use a dot chart to represent sort of how people fall in this spectrum. So I'm loading that up. You're going to need to download that data from the website to use this. I'm going to pull out the votes and then do a little. I'm going to glue the senator name and the party together to get our labels, and then I'm going to ignore all of the individual votes, but just come up with a sum. Each person will be described by how many times did they vote right, according to the AFL-CIO. And so we have these values. So I'm going to make this into a dot chart. If I do this here, it's okay, this doesn't look bad. I don't have any labels on here, so it's hard to tell are these columns or rows. Really, they're supposed to be rows. There's a row for every senator, but it's really hard to read, even if we had labels. Here I can put labels on it, and you can see, well, that's almost impossible to see. Maybe if I cleared this and tried it again, well, still not very good. Maybe if I zoomed in or something, I could get it to work, but you can't read this. But this starts to show something. You can organize it into groups by party here. And so that's what this actually now starts to look interesting. I can't read these, but I can tell that almost all of these appear to be R's. Well, I'm organizing by party, so all these appear to be R's. All these appear to be D's, and we see a few people who are sort of in the middle in each party. And then this independent person is sort of more close to the Democrats than the Republicans. And if I move things around a little bit in terms of the size, this actually, for something this big, is sort of readable. And this could be a nice way of representing these parties. But the thing is, within a party, there's no real order here. So maybe I want to, instead of looking at party, ignore the grouping and just have a single group, but order them by how much they are in agreement with the AFL-CIO, and then I'll use color to indicate the party. So I'm going to first find the order of the votes. So this will help me rank order this from least to greatest agreement. I'm going to do a new dot chart, and every one of these things I'm going to put it in this bracket order, so it sorts them in the order of their voting. And then I'm going to use color, and this is a little tricky to get right. I have 3 colors: blue, maybe I'll change this to black, and and red. So blue would be Democrats, black would be independent, red would be Republicans. And then I'm going to put it in the order. Well, I'm gonna use this for V2, which is the party, which is going to be 1, 2, 3 because it's a factor, in that same order. So now if I do this, you can see that it's sort of monotonic here. It's monotonic here. The independent is here, Jeffords, sort of in the middle. You can see there's this region here where there's a little overlap between parties, but not much. There's some people who are very zero votes with the union. There's some that have a complete agreement with the union. And it's small enough that I can actually use this. I can use this line to go find where they live on there. And and you can see in the, when I plot this and put it in the book, it's, let's see, I think this is when it appears for, maybe it's here. That's actually not too bad reading. And if you have a big enough web page or have the right proportions, this would be a nice way of showing a lot of data in one graph. Okay, so that's a dot chart. The next thing we want to talk about is error bars. Publication manuals recommend that when you make a graph, you should put not just the mean, but some indication of the variability of that mean. There's a lot of different ways of doing this, and we'll look at just two. One is a calculation of standard deviation, which you can calculate with the SD function. One is a calculation of standard error, which is essentially the standard deviation divided by the square root of n, which means if you have a lot of data, your estimate of the variability of that mean goes down. The standard error is your estimate of the variable of the mean. The standard deviation is your estimate of the variability of the data. So you could expect, if you have a lot of data, you have a really good estimate of that mean. It's very small. So here's just some data. I'm going to calculate the means, the standard deviations, and standard errors. So for a set of 5 groups, those are the means, those are standard deviations, those are standard errors. And I'd like to draw error bars on these. So here is sort of the raw data, and here are the means. So you wouldn't necessarily be able to tell just by looking at the data that it's increasing because it's really noisy, but it is increasing. Well, how good of an estimate are these? That's sort of what we want to know. Well, that's one thing you want to know. You may also want to place on here how variable the data is. So if I didn't have these dots, you'd know that, maybe this is one standard deviation, so you can visualize the range of people. Whenever you do some type of error bar, it's important to indicate what it represents, and oftentimes people don't even know their graphics package does something and they just assume it does something reasonable, but a lot of people have different interpretations of what the right thing to do is. So we're going to do standard error, and we're going to do one with plus or minus 1 standard error, and a really lightweight way to do this is with the arrows function. So arrows draws arrows, but there's a couple things you can do with arrows. You can change the angle of the arrow so that, let me do sort of a standard arrows command here. I'm going to look at the first mean, and I'll ignore all this other stuff. So the arrows command will generally draw an arrow from one XY point to another. So let's see what happened here. It drew an arrow from here to here. Now, if I fold these, I guess, so they're at 90 degrees, and I put that on either side, that turns into an error bar. That fold is what I get by specifying angle equals 90. Code equals 3 specifies that I want the arrow on both sides, and then I can, length specifies how long that arrowhead is. This is way too long. So by putting these things together, here is my error bar. And here I can, instead of using standard error, I can use standard deviation. Here probably the length is a little too long. Even if you zoom in, it seems a little awkward. I still have that old arrow here, so none of it looks that great. But that's drawing just one. So I know that I have means and I have SDs, and so I want to draw the standard error from x equals 1 and y is equal to this plus this, or this plus this to x equals 1 and y is equal to this minus this. That's what this command will do. You'll see 1, that plus the standard error, 1, that minus the standard error. And then putting the bars on both sides and making it smaller gives me that look. But I can do this for the whole data set at once in one fell swoop. We've done this a number of times now, so here's the points. And now this arrow command drew all my error bars at once. So what happens is each one of the arguments has 6 values. So here I have 1 through 6. Then I have the means plus x. So then the next point is going to be all of these heights. Then I'm going to do 1 through 6, which is the x values again. And then finally the means minus the standard error, 6 of those values. So I put 6 values in each of these 4 arguments, and it draws all 6 of them at once. This can be a little fussy to get right. Sometimes you do this and you get lines drawn everywhere if you get it out of alignment, but it's a lot easier than making ultimately it's a lot easier than making a loop and drawing them one at a time. But if you are a little scared about doing this, go ahead and make a loop of this command and put I in there, and then loop I 1 through 6, and it'll do the same thing. It's just this is a little more verbose doing it that way. So that's a handy way of doing it. You can also, I've done this before, I've used boxes. The rect function works very much the same, except instead of specifying just the top and the bottom, you specify the upper and lower corner. And so I can do the same thing here. And now this is probably more like a standard deviation. I make this bar showing plus or minus 1 standard deviation. Now it's more like a box plot, like a hand-drawn box plot, and it still represents that range of data. And that's fine to do as long as you label clearly what it is. So those are the ways of doing it by hand. There are also a few functions within libraries that will do this. Certainly something like ggplot will do some error bars for you, but I find that a lot of people don't know what it's actually doing. It draws something, but oftentimes it's not probably what you think it is or what you want, and so you should just look in, if you're going to use ggplots error bars, you should look into so you know exactly what they are. These are, I guess, annoying because you have to compute it by hand, but they're nice because you know exactly what you're doing, what you're computing. So you have to install a package, and you can try to install both gplots and plotrix. You can do this with a command like this, and then I already have loaded it, so it's going to download it, and it'll ask you, do you want me to restart? I'm going to say no. You can also, so it's going to download it and install it. You can also install it through here. If you go to install and type plotrix, it'll do, and gplots, it'll do auto completion, and you can install it through here instead of this. And I like to comment these out so that you're not always installing it. Just because it's installed doesn't mean it's available. So you also have to load the library. So this just makes sure it's on your computer. This library function makes sure it's available within your R session. So I'm going to load those. Now it turns out that there's each of them has a function called plotci, and I think one was based on the other one, but then they diverged. And we can look, we can try to get help on each of these what they look like. They have slightly different syntax though. So if I want to run plot.ci, I give it my x values, I give it the means, and I give it the standard errors. And this is going to be the first plot.ci load. So I think this is the gplots plot.ci. And that's what it looks like. So it does this all at once. I just give it, I don't have to give it a plus and minus s standard error. I just give it the means and the error bars, and it does it all for me. So that's nice. So if I want to specify specifically which one I want, I can reference it with this : so library : function. I'm going to plot these next to one another. So here are the two, and this gplots makes this gap in here by default, which I think oftentimes doesn't look very nice. But you can fix it up, or the plotrix one with enough things, you can specify size fractions and colors and things like that. And this looks pretty nice. You can have each one be a different color. The gplots one offers something called plot means, which rolls it all together as well and does some other things. So if you look at what happened here, it makes the line, it makes the error bars, it puts a gap between there, also labels the n and things like that. So that might be another handy way to plot it all at once. So there's a number of built-in plot confidence interval functions that you can use if you don't want to use arrows by hand, but you do need to make sure you load those libraries and have them accessible. Now you can also do this for error bars, or for bar plots. So here's a bar plot. Maybe I want to put error bars on this. So can I do a plot.ci? Well, I can if I say add is equal to true, so it'll just add it on. So this is, I mean, it's the same numbers. It's not quite right. You can see that these lines, they go outside the region of the plotting. I would like to fix that. And they're not centered because remember the bar plot values are not 1 through 5. It does its own organization to do that. So we can do this again. And what I'm going to do is it's going to return the x values. So I'm going to take new x as what the x values are. And I'm going to specify the y limit. And so I don't have to calculate it and hard code it. I'm going to say the y limit is going to be between 0. I want it to bottom out at 0. And the top should be the biggest x value plus the biggest standard error. So it's going to be higher than the biggest x value plus the biggest standard error. That's not exactly what you want, but you want a little, maybe you want a little more headroom, or you want the max of the sum of these two or something like that. But this seemed to do a good job. So if I just print new xy, it shows me here the xy values. So I can use that in the x of plotrix plot.ci. Line width 2, so it's a little chunky. I've got x, the actual values of these bars, the standard error values, and then I use add equals true to add it on. So this is a little nicer, although now the black and the blue don't fit well together. But on the other hand, if I make them white, then the white and the black don't fit well together. In some areas, what people do is just do one-sided bar plots, or one-sided error bars. They'll just plot the top. But here's a trick you can try. So I'm going to do the same bar plot again, but now I'm going to plot CI twice. First time I'm going to plot something that's white and make it LWD, stands for line width, and make it a little fatter. And then I might even make this smaller. I'll plot it again on top of that. So now if we look at this closely, you can see how you can see it up above and down below. You've kind of got this erased version below it and this unerased version above it. So that's just by overplotting twice. Of course, I could have changed the color of this, but maybe I like navy blue. Okay, so that's a few examples of making error bars by hand or with one of a couple built-in plotting functions. Our next topic is to do a little more advanced box plotting. We looked at box plots like this before, where you have a distribution, and it's conditional on the levels of some other variable. But you can do it. Here's tooth growth, for I think these are gerbils or hamsters, and we look at tooth growth by which supplement they have and tooth growth by how much of the supplement. And you can see there's different distributions and different effects of these. You can actually do both of them. So instead of doing length by dose, you do length by sup plus dose. And everything else is the same. And it recycles colors here. So I gave it two colors, gold and gray. And so now this color is going to be associated with the vitamin C is gray and the orange juice is orange. So the color here I'm using to help show what these labels are. I could do it the other way, but then my colors are bad. There's an exercise to fix the colors here. So it's easy to, this looks okay, but then you say, well, what is these three things? What are these three things? Why is this yellow and these two are yellow? Well, the answer is I only use two colors. So you can, it's just going to recycle the colors and lay them on the different boxes in whatever order they come in. The other thing with this is wrong. The other thing with this is these labels are just taken from the data frame and they're not really very readable. So maybe we want to do things to make them a little more interpretable. Maybe by making it sideways, I have more room to write the labels here. That would be one way to do it. Or maybe I've got even more data. I have like two sets of this, one from gerbils and one from hamsters. So I'm going to, I want the box plot of two of them, so I can use the supplement times dose times the repetition. So I've just, if we look at tooth 2, I've doubled it and I've added another variable, repetition, and I can make box plots by 3 variables. So this gets a little excessive, but I drew this line here to help indicate that it's 2 different repetitions or something, and maybe this would be gerbils and this would be hamsters. It could be labeled up there. Here the colors are still going to be recycled, so those colors are appropriate. Or you could add text, and here's sort of a way of adding text to 3 locations at once by using separate, I'm saying this is dose 0.5, this is dose 1, this is dose 2. The legend here didn't really show up, so I'd want to fix that if I were using it. Maybe if I get rid of this and try this again. Okay, so now the legend looks better. So this might be a good way of representing all 6 things. This shows that there's these cells, and these cells. Color indicates what type it is. And actually I could use arrows and make a little bracket up here. I could use the arrows function to do a little bracket as well, probably, to help, or draw lines like this to indicate that these are grouped, and these are grouped. All right, so those are some thoughts about making a little more complicated box plots than we did before. It's nothing really difficult, but just recognize that you need to figure out ways of labeling it as you get more and more variables that you're trying to organize box plots by. Okay, next we're going to look at how to use JPEGs and GIFs and other rasterized images in plots. And every time I try to do this, the libraries change a little bit. These are not built in, but I've used a bunch of different libraries to do this in the past. So here's just one example of how to do this. We're going to use the JPEG and the Bitmapped libraries to do this. So install these. I'm not going to restart because I actually have them all loaded. But there are other really complicated advanced image libraries available as well, but these are very lightweight and very simple. So again, I'm going to run library to load these to make them available. And we're going to plot images from the Brady Bunch. This is the zip file that I had you download. So if you have this image as zip, unload it and make sure all of the things are in this folder. So here was the zip file. I unloaded, I unzipped it to images, and there's a bunch of pictures of the Brady Bunch in there. And so first I'm going to load these with the read JPEG, and this will read them. And then I have, what I'm doing is converting from this image file to a pixmap that the pixmap library can recognize. And it gives me, let's see, it gives me some warnings, but everything works out okay with this code. So I have this list of images, or this vector of images, and every time I load an image, I transform it, and then I add it to the end of this vector. So this vector grows by one element every time. So now if I look at images, unlike a set of numbers, it's actually 10 pixmaps with these weird representations it's plotting out. It says me the size and things like that. So I can then I can plot these using the add logo function. And add logo sort of makes a stamp of a pixmap on any regular graph. So I'm going to start by just making a blank graph. You can see I said I made a blank graph that is between 800 wide, 600 high. I called it type equals n. That makes an empty graph, and so nothing else is plotted. Then I'm going to plot a black background with this rect function. And then I'm going to go through each of these and plot it in a random location. And this takes a little while to do, but you can see, let me try to run the whole thing again. Apparently, okay, we have it here. It took a while to plot it, and it's going to take a while to show up. So here is my graphic that has all of the Brady Bunch, including, I'm not sure if it's going to show up if I zoom in. So what it's doing is it's treating every pixel as a piece of data. So there's, millions of pixels here. It's not doing it very efficiently, but if you have an image that you want to put on a plot, you can do that using the add logo and add some more interesting imagery to a plot if necessary. All right, the final thing we're going to look at is sort of an advancement over box plots that I end up using a lot because they show a little more than box plots. They're sort of a vertical histogram. They're called a violin plot. They're called this because they sort of look like the outline of violins. We're going to try it from two different libraries. So you're going to install Vioplot and Violin mplot. So take a moment to install those. And then also make sure you load them with the library. So they work differently, and the Vioplot is a very simple one, and what you do is you give it a distribution of values in each argument, and you can give it as many arguments as you want. And then I'm going to do some formatting. I want it to be gold, and here's what the labels should be. And so in this case, V1 is going to be our orchard spray example. So if you remember, we have orchard spray and how much of a decrease or in bugs or a decrease in bees or something that we saw as a result of these sprays. And so it makes a little tiny box plot in the middle, and then it sort of does a smooth histogram to show you the shape of that distribution. Both of these libraries have a little wonkiness, like Vioplot, I couldn't get it to make a title very well, so I'm going to add that separately. I could also use a matplot to plot all of the individual points. So this looks pretty nice. You can see both this shape of the distribution, and you can see every individual point. You can tell that actually there's not very many that make this up. These long bottles sort of look like are there because of this one outlier. And you can also see, well, there's some smoothing going on here. And so that smoothing, whatever it's doing for smoothing, might be hiding things as much as it's showing things. It might be making us see things that we might not otherwise have seen. and might not really be there. For example, how smooth it is depends on some algorithm that does the smoothing, and what really it does is it takes like a Gaussian and convolves it with your data, and depending on how wide that Gaussian is, it sort of adds a bunch of normal distributions together at the points of your data. And if you add a bunch of small normal distributions together, it might look like this. This doesn't look anything like any distribution you really care about. It's added a little bump at every point. So this would be a bad idea. You'd want it smoother. So there is this way you can control it with the h value. You can try it. You can try, that was h equals 2, and h is really depending on these values. So if I make h equals 50, really you just see boxes, and that doesn't really represent it either. So there might be a sweet spot you want to choose. Violin mplot is a different library created by different people. The arguments are different. You just tell it all the data, tilde all the treatment levels, and it makes all of the levels. So much more like a traditional box plot. And it doesn't, as far as I can tell, let you specify the smoothing parameter. It tries to pick a reasonable one. And this one doesn't look bad, but I don't know how it looks in other data. And furthermore, it looks different than anything we saw in the other one. So not every violin plot is the same. So you shouldn't, you've got to sort of know how it's being created. And as I said, it could hide as much as it reveals. One problem with these is if you're using maybe one of the most common types of data collected by humans about humans, by psychologists about humans, if you're using Likert scale ratings. So how much do you agree with a statement on a scale of 1 to 5? I know we all do these all the time for different companies or teacher ratings or whatever. And so you might have 5 levels here, 1, 2, 3, 4, 5, and but it's just going to be a bunch of bins. So if you smoother, if it will either smooth it nicely, but that will distort it a little bit, or it will do something like we saw here. Well, it could smooth it like this, or it could smooth it like we saw here, and you'd only see a bunch of bumps. So there could be problems. Let me load this function here. Here, this is just basically a copy of the Vioplot function with some changes I've made. So if you want to know what the code associated with Vioplot is, I can just type Vioplot without parentheses, and I'll spit it out. And then I can copy this down here and make my own function where I tweak things. But let's first start with sort of a fake data set of responses. Here is what you might get out of a survey. You know the gender of someone, you know and you know how much they agree or disagree. So that's all you sort of have. You have asked a bunch of people, how much did you like this course? And I'm going to associate a written response with a value. So we want to make a violin plot of this to show what the distributions look like. And if I were to do it with a traditional Vioplot, well, because all of the data are only at these integers, I get these wavy violin plots, which kind of looks weird. If I can change the h and make them smooth, but this might be a lot smoother than my data really are. Or I can make it really small, and then I get these sort of scalloped functions, which don't look right either. So I thought, I was doing this for some project, and I thought, what I would really want to do is no smoothing at all and just draw the polygons surrounding it. And so I took the Vioplot function, and I really didn't have to replace much. I dug into where it's doing the smoothing, and I removed that smoothing and wrote this new function and added a few other things. So I called it vplot2, and now here's something you could use for plotting data like this. So it's not smooth anymore, but that's actually what you wanted because these are the actual true values. This shows a real histogram of the values at each level. I also have other things like how many are in each one. So now I can really see, oh, there were 1,000 total. Men gave slightly higher ratings than women. I can also see how many are above 3, which is this neutral, 4% above 3, 10% above 3 or something, which is how many are in this upper tail. What is the mean? And there's also this don't know here, which by looking at setting the ignore values, I could get rid of. So I don't, unless you have data like this that you want to use this, you don't need to go into all the details of this, of how to use this, but it's just recognize that for any of these functions that are built in libraries, if they're good but not perfect, you often can make your own version. Get the look at the code, make any tweaks you want, and update it to make your own data visualization function. All right, so that's it for this chapter of graphics. We have one more major chapter of graphics, and these involve a lot of special purpose libraries, sort of like Violin plots, but for other sometimes very specific types of data, and also a lot about how the R color system works. So stay tuned for that.